some announcements. The second homework assignment is due on Thursday, and my goal is to grade your first assignment tonight or tomorrow. And so just like the earlier assignment, you should upload the PDF file for homework 2 to Blackboard before class on Thursday. And then on Thursday, we're going to be doing some spreadsheet work in class. And so bring a laptop that has Microsoft Excel on it. And if you don't own a laptop, you could borrow one from a friend, or you can check one out from the library. They have extra laptops there. And if you have a laptop but don't have Microsoft Excel installed on it, remember that you get access to the Office 365 apps, including Excel, for free by virtue of being a tuition-paying student at Marshall. So bring a laptop to class on Thursday. You'll have a very boring day just staring at everyone else doing fun stuff if you don't bring a computer, because it's going to be really fun. All right. Any questions on the announcements? I'm not being sarcastic either. I think Excel is about the most fun you can have. So. But I guess that's why I'm standing here in front of a computer screen. All right. So what we're going to do is pick up on these example problems from last time. We ran out of time on Thursday of last week. And so the first one, let's just look at this. We are trying to see what is the present value equivalent as a lump sum of an annual series. And so if we were going to summarize this one in the shorthand that we've been developing, we'd say that this is find P given A with the interest rate of 8%. and n equals 3. Sometimes you have to prove it to yourself because you see 4 arrows, 1, 2, 3, 4, and so you'd be forgiven for, wanting to pause for a moment and like refresh your memory on why it's 3. It's because what we're doing is we're converting 3 equal payments of $12,500 to a certain lump sum that we'd need to deposit today in order to fund an economic equivalence of those of those payments to us. Okay, so if we go to the table, let's see. I think that the factor lookup table for the 8% is 2.5771. So sometimes what we'll do is just take what's in the parentheses there and make it equal to the factor. And then what that effectively is saying is that the present value is the annual amount multiplied by 2.5771. And so if our annual amount is 12,500, and we're multiplying it by 2.5771, then what we get is a value of 32,214. And can you double check that for me with your calculator to tell me whether I've done that math correctly?
I got 32,213 and 75 cents.
Ah, okay. So you got 32,213 and 75 cents. All right. That's what you get if you multiply these two things together. Now, we've got 1, 2, 3, 4, 5 digits in our factor, which means that we should report our answer to 5 digits of accuracy as well. So when you put it into the calculator, and this is what you get, you need to count how many significant figures do we have. 1, 2, 3, 4, 5. So we should report the answer to the nearest dollar, which is why I've rounded up from 213 and 75 cents up to 214.
Do you always round up? Well, no, that was a poor question. If, like in numerical terms, over 5, you would round up, or like here you're over 50, so you would round up.
Yeah.
But for some reason, I have it stuck in my head that in 222, you you only had $213. You wouldn't have like the extra 25 cents, so you kept it at 213.
I think you may be thinking about the break-even calculations where we're doing it row by row. So I think I know what instinct you're talking about, and we will revisit that. But here you would, like if it had said, and 25 cents, I would have said 213.
Okay, so that answers that. Now say that we had 7 significant figures.
Mhm.
So we were reporting to the nearest penny.
Yep.
And say it was that, and then you had a 6 beside your 5. Would you round the 5 up to 76 cents, or would you do 70? Because I just have a hard time comprehending.
Yeah, you'd round it to 76 cents.
Okay.
Yeah, there's nothing magic. This is just normal rounding.
I just thought that where you couldn't have like a fraction of a cent. where
No,
it's
the only thing it would be, like, we'd maybe be a little bit more careful about it, is if you're using a factor to find out, like, what's your mortgage payment, and then, like, the very last mortgage payment you'd owe different than all the previous series. So, like, maybe it would be $1 or $2 difference, that last payment. But this is just normal rounding.
Okay.
Yep. All right. Good. Now, the other one that we have 11.5%. Use the equation method to find A. So let's find the equation from our list. Let's see, I've got the handout here from last time. So we would summarize this as find A given P at I equals 11.5% and N equals 3. Okay, and that's equal to, so here in the formulas, we want to find A given P. So that's the capital recovery formula that's provided. So the capital recovery formula, I 1 plus I to the N minus, I was looking at the denominator. So I plus 1 plus I to the N, 1 plus I to the N minus 1. So that's our capital recovery formula. And so if we just substitute in the values here, 0.115 times 1.115 to the power of 3 divided by 1.115 to the power of 3 minus 1. Then in the numerator, that's going to be 0.1594125, and so on and so forth. In the denominator, 0.386195, and so on and so forth. The digits continue. I don't round it off in my calculator because I want to know the overall factor, 412776, and so on. So then the amount that we should pay on an annual basis is the principal, the present value multiplied by this factor. So A is P times the factor. So A is the $7,500 multiplied by 0.412776, and so on and so forth. And it turns out to be $3,095.82. So just to bring that up on the screen so we've got it in the recording. Here's all the various substitutions that we've done, and we're accurate to the nearest penny and fraction of a penny if we want it, but...
So here we can run up again?
Well, here, because this was the equation method instead of the factor method, we can be accurate to the nearest 1 cent. So we don't have to do any rounding on this one. Yep. No rounding is necessary. Okay, so any questions before we move on from that one? All right. So today what we're going to talk about is first we'll look at some reminders about the gradient. Remember, the gradient is when there is an increase of a constant amount in each subsequent year. And so the strategy that I told you when you have a gradient that starts at something other than g is that you should effectively think of it as an annual series and a gradient together. And so this is just illustrating that point we talked about last time, that when you see a combined annual series and a gradient, then what you can do is either in your mind or sketching it out on paper, separate the two components of that. So we've got a gradient and an annual series. And what can be even more deceptive is if the annual series and the gradient are in opposite directions. Think about what that would look like. What if we had an annual series that was up and a gradient that was down? So what we'd see is, here's our cash flow diagram, and in year one, maybe it is the 400, and if G is 30, then in year two, it would be 370, and then 340, and then 310, and so it's getting less each year in a case like that. It's the same thing. We could just think about it as we have an annual series where every year is 400, and then a gradient which doesn't begin kicking in until time 2, so nothing in year 1, and then in time 2 is 30, 60, 90. And so that's 0G, 1G, 2G, and 3G. So that'd be a real tricky thing that I could pull as on a test or something, give you an annual series that's one direction and the gradient that's other direction, and maybe offset it from time 0. And so that's what the next strategy tip is about. So by the way, before we move on from this slide, does anybody have questions about the idea of a combined annual series and gradient? Okay, so now this is that other case where, what if the cash flow diagram is offset from time 0 by several years? It's still a gradient. There's still a gradient here. And, it could have been this, offset by several years. But the strategy, like your problem-solving strategy, you've got two approaches. One is you can take everything to year 8 with find f given g, and then from 8 to 0. That would be one approach. Or another might be to take everything to year 3 by pretending like year 3 is the so-called present. So I've got that in quotation marks here because we know it's actually year 3 because time 0 is here. But just briefly, we're going to think about year 3 as the present because that's the form of a gradient, is that we begin seeing the effects of it 2 years after the so-called present. So we could find a single lump sum in year 3 and then move that lump sum from year 3 to year 0. Okay. So that's just so reinforcing the problem-solving approach and strategy. I'm going to give you a new set of problems on Thursday, and it will include a couple of gradient calculations and also multi-step problems where you've got a time offset like this. So if it's an equation method problem, you can use these formulas. So for example, finding the present given a gradient, boy, that's a complicated one. Or finding future given gradient, I don't know, maybe slightly less tricky. But gradients are challenging problems. All right, so now let's move on to the second part of our class today, where what we're focusing on is So far in all of these, we were talking about what if we need to find P given G, or, you know, in this example, we were finding A given P, or find P given A. But in all these problems so far, N was known. It was just one of the givens, and so was the interest rate. But sometimes those are unknowns, and that's what we're going to be focusing on today is what does it mean when the interest rate is unknown? And what it comes down to is the idea of balance, because there is a certain interest rate out there that will make the inflows and the outflows equal in economic terms. And so if you have a balance between the present worth of the inflows and the present worth of the outflows, then that is a really important interest rate. Finding the interest rate which brings balance between the in and the out is the rate of return for a project. And so sometimes you're having to find for what is the interest rate that would cause the inflows and the outflows to be equal. So whether this particular cash flow diagram is in balance depends on the interest rate. So let's count how many years are there. 1, 2, 3, 4, 5, 6. So 6 times 5,000, it looks like there's $30,000 that get paid out over time. But remember, $1 in year 6 isn't the same as $1 in year 1. So we don't know whether this cash flow is in balance until we know the interest rate. Or maybe putting it another way, should you do this? What if you had to pay $23,000 today, and then what that means is that for every year, for 6 years, you get $5,000 back. Well, should you do it if you live in Germany where inflation is really low? Maybe. Maybe that would be a good return. But should you do it in Venezuela where inflation is very high? Probably not. Or Zimbabwe where inflation is much, much worse? So there are places where the interest rate couldn't justify a present investment if the future values are relatively modest like this. So what we're going to do is we're going to calculate the unknown interest rate that brings balance between the inflows and the outflows. Okay, so in these problems, this is our approach, our strategy. You'll either have a table or a cash flow diagram, and all the amounts that are in the future, we're going to take it to time 0, to the present. And we'll combine it with the amounts that are already at the present. So usually for business opportunities that you're considering, what you would have to do is you'd have to pay something now, and then the revenues you're going to receive are in the future. So, I mean, think about when Delta Airlines buys an airplane. They have to pay millions of dollars now, and then they make their money back over years and years into the future. So a lump sum payment now entitles you to future revenues that hopefully will be profits, and it justifies the original investment. So you're combining the discounted future amounts. They've been discounted to the present. So this verb here, discount, that means moving money from the future to the present. And then what we're going to do is we'll start off with a guess of the interest rate, because this whole problem is the interest rate is unknown. So we'll try out what if we're discounting those amounts at 1% or at 2%. We're going to try lots of different interest rates, and we're going to keep changing the interest rate that we use for the discounting until we find balance between the inflows and the outflows. So when those two are equal, that tells us we've solved for the unknown interest rate that brings balance, and that is your rate of return. Okay, now since we're going to be using Excel a little bit today and more starting on Thursday, there are these built-in functions that Excel provides. And Excel automatically assumes that if you give it a positive amount, that it should return the answer as a negative amount, because it thinks if you want to withdraw some amount in the future, then you should need to deposit it today. So when you put amounts into those functions that Excel has automatically built in, it changes the sign on you. And you just need to be aware of that. That assumption isn't bad. It's just that oftentimes we have to manually override that assumption because we don't necessarily want to change the sign. We just want to change the quantity of dollars based on how many years back we are discounting it. So Microsoft Excel assumes that if you give it a number, it should give you the negative of that in a different year. So if you instead just want to know the same direction, so if it was a withdrawal and you want to know how much is the withdrawal, but just in terms of year $0 instead of in terms of year $3, then we'll just insert the negative sign into the function when we do that. Okay, but before we do Excel, we're going to take a look at some problems where I'm going to ask you to discount this cash flow situation at both 10% and 12%. Just to illustrate, the break-even point is between them. Okay, so I've given you the handout, and it also has the factor tables. The factor table for the 10% and for the 12%. So I'm going to pause for a moment. I'm asking you to sketch this out, the cash flow diagram. It doesn't say whose perspective, and so just assume that it's from the contractor's perspective. Now this phrase net present value, that just means take everything to times 0. All right. Feel free to collaborate and discuss with one another. So as I was circulating around, it seemed like everybody had the cash flow diagram looking pretty good. They had the arrows up for the annual series because it's providing income in the future. So here's A is 16,000. Each one of these arrows are the same height. They're consecutive for 5 years. And then a payment of 60,000 today. So this is the cash flow diagram. Now in part B and C, what we're basically doing is we're asking, what if this person had to borrow the money from the bank? Should they do the project? So if this person borrows the money from the bank and pays 10% interest, then what that means is when we combine everything together, if we discount the future revenues to times 0 at 10% interest, then that means that the sum of the profits is $652, $652.80. But if this person is discounting at 12%, what that means is that the future revenue isn't as valuable if you're discounting at 12%. So the future amounts, when combined with the 60,000 that's already at times 0, which is kind of the acquisition cost of the equipment, then you're going to get a negative net present value. So the way that you could interpret this is the project is profitable if you can borrow money at 10%, but the project is not profitable if you have to borrow money at 12%. So this is one of the ways that we can give a thumbs up or a thumbs down to investment opportunities, is you'd compare your minimum attractive rate of return to the rate of return that you expect to make on a project, and if the project offers you more than the minimum attractive rate of return, then you could give it a potential thumbs up. But if you're discounting the future revenues at some interest rate that then gives you a negative net present value, you should never do a project when the value of the project is less than zero. Like if you're losing money for doing the project. So in technical terms yet, we haven't found the unknown rate yet though. So far we know that the rate of the project is between 10 and 12% because, you know, this slide of the balance, if you think back to that, what we want to do is we want to find out what interest rate makes it so the inflow and the outflow is equal. That's what we are aiming for. And so it's somewhere between 10 and 12%. The interest rate that would make the sum of the annual worths equal to, you know, when discounted to time zero, equal to 60,000. So before I move any further, does anybody have questions so far? Okay, well, let's look at the procedure then. If we are going to use Excel to solve for the interest rate. If you have your computer with you today, feel free to get it out, but that isn't strictly necessary. If you just want to observe, then that's fine too. So the first thing I'm going to do is I'm going to set it up just to see if we can get Excel to confirm the answer that we got, like the $6.52 and 80 cents. Let's see if Excel agrees with that. So just starting from a blank workbook, what I'm going to have is I'm typing in I equals, and I'll start with 0.1, which is 10%. Okay, now below that I'm going to have a column that I'm calling year, and I'll have a column which I'm going to call amount, and then a column which is PV of amount. Okay, so now we're going to translate our cash flow diagram into a cash flow table, which you've done before. So how many years are there in this cash flow diagram? 5 years. All right, so we'll start at 0, 1, 2, 3, 4, and 5. Okay, so the amount at time 0 was an outflow of 60,000. So I'm putting negative 60,000. Need one more 0. Negative 60,000, and then it was inflow of 16,000 each year in years 1, 2, and beyond. So you can just type those in, or once you have 2 of them, if you highlight both and then click and drag in this corner, you can drag it down and it will stay the same. If you only start with 1 and you begin dragging down, then it's going to start counting. Oh, let's see. Oh, okay, well, it knew to stay. Sometimes it'll say like 16,001, 16,002, 16,003, and so on. But what we want is just basically to translate the cash flow statement into a diagram, and then from the diagram to the table. And the first part of the problem said, well, what about at 10% interest? So 10% interest is 0.1. So now I'm going to use a function that's automatically built into Excel. It's called the PV function. So equals is how you begin a formula, and if you type in PV, then it's going to start to give you some hints on what needs to be in that formula as hard as you do P equals PV and then the parentheses. So you can see that the little formula hints have popped up beneath there, and it says first of all it wants to know about what rate to use, what interest rate. So I'm just going to click in the location where we've got this interest rate. And I'm also going to press the F4 button on the keyboard. And it will put in dollar signs before the B and the 1. That's called anchoring the cell reference. And when you press F4 and anchor the cell reference, then it's just always going to look at this location as the interest rate. Even when I drop the formula down in different rows, it will always look at this location for the interest rate. Okay, so now I'm going to do a comma. And this is saying NPER, which means the number of periods. So for instance, this 60,000 is already at time 0. So it needs to be discounted 0 periods to the future. this 16,000, which is in year 1, how many periods does it need to be discounted to get to the present? 1. So I'm just going to always refer to this row, the year indicator for whatever row we're on. Okay, now I'm going to do a comma. Now it's asking, is this a recurring payment or a single lump sum future value? And in this case, we're going to treat each one of these arrows as an individual lump sum that we're discounting to times 0. And so I'm going to skip over the payment field by just putting another comma in there. And then, so now it's highlighting this FB. I'm saying minus, and I'm using the amount quantity. Okay, so the expression inside the parentheses is the interest rate, the number of years to discount, or I guess number of periods, because a period could be a month. So it's interest rate, number of periods, skipping over the payment field, and we'll see more about this payment thing in the future, so don't get too hung up on that. The point is we want this B4, the amount, to be in the field that's associated with a future value. All right, now it's red because it's an outflow. And let me just select all of these right now and change it from general formatting to currency. I think that the currency looks the best because the red thing, that's a little distracting. I'd just rather have the minus sign if it's a negative. And you'll notice that it's also put in the commas and the cents and all that. So I like the currency formatting, but that's a matter of personal preference, I suppose. Now that we typed that formula in, we can drag it down through the rest of the rows, and it automatically is going to do some calculations that are pretty interesting. What this has done is it finds out the $16,000 that's in year 1, what is the value of that in year 0 if you discount it at 10% per year. So in this row, it's basically just doing future equals present 1 plus I to the n, or I guess we could say present equals future 1 plus I to the negative n. So what we're doing is we are finding, for example, 16,000, 1 plus 0.1 to the power of 1, oh, minus 1, right, negative n. So it's finding out the present value equivalent of 16,000 in year 1. So if 10% is the interest rate, it's the same to either get 16,000 1 year from now or 14,000 today. Or if you're having to wait 2 years, if I told you you can either have $13,223 today or $16,000 2 years in the future, and your internal interest rate is 10%, then those two things are economically equivalent. So the reason why these amounts are going down is that if you're having to discount this amount in year 5, you're moving it 1, 2, 3, 4, 5 years. Every year you move it back in time, it's losing 10% of its value. So if you're moving it back 5 years and it's losing 10% of its value with each step, then it's not going to be as worth as much as this, which only had to move 1 year back in time to get to the present.
And if you take a sum of the present value, would that give you your net present value for the project?
Yes. So 6.52 and 59 cents ought to be pretty close. 6.52 and 80 cents, and I guess the difference being that I was using the table lookup. So you know, there's a little bit of round off error if I was using the table lookup compared to ultimate precision. So what he was saying is the net present value, which is the thing it's asking for here, the net present value. That means combine together all of the things which have been discounted to the present. So we want to find out the present value of the revenues and the cost, which was already at the present. Combined all together, the project is profitable at 10%. But what we found from our hand calculations is that the project is not profitable at 12%. And watch, if we change this from 10% to 12%, then now it's a negative value. And that's consistent with our hand calculations which said negative 2323. Yeah, there we are, negative 2323. So we're losing money if we're at 12%. So balance, equilibrium between inflow and outflow, is when we can find there's a certain interest rate that will make this sum equal to 0. So let me write that here. What interest rate will make this equal to 0? So I could just play around with it a little bit. You know, 10% is too low. Well, what about 11%? I think we've already gone over the line. So it's somewhere between 10 and 11. Let's try 10.5. Okay, that's pretty close. Let me show more precision here. 4.5. Closer. 4.0. About the same, right? 2.5. Oh, that's very good. We could do this all day. I mean, it wouldn't take us all day to get to the nearest penny, but super fans of Excel will know that there's a tool for us which will automate this process. Is there a question before we move on?
Yeah, I got Mac and the F4 key didn't work for me, so I was just waiting for you to complete and then help me out.
Okay, yeah, we can take a break for that. If the F4 button doesn't do it, you can just type those $ in manually.
Okay.
Yeah. So you've got an Apple computer.
Yeah.
I think you need to maybe press like with an Apple computer to get the function keys. I think it's like, oh yeah, I mean you should just be able to press F4. I think.
I have a Mac.
No, is it Option or Command F4?
Command F4 doesn't work.
Well, just type in the $. So $B, $1. What is it, Victor?
I think it's function F4.
Did it do it? Good man. Good. Jace.
Is there, it's kind of a weird question, but is there, I guess like a linear, like proportion between the interest rate and the net present value?
That's a good question. Let me skip ahead. It's not linear. It's not linear because of compounding. I think I've got a figure somewhere that shows. Yeah.
You should have done like the first day class.
But it's still pretty close though.
It's pretty close. I've got a figure, boy, I didn't think it was this far into the semester, but there is a figure that illustrates that. Yeah, you could, so you're thinking, could you just do like a linear interpolation?
Yeah, because I just did, that's how I got
You-
2.45.
You get pretty close with linear interpolation. Here it is. All right. See this curve? Yeah, so if one interest rate gives you a positive present worth and another interest rate gives you a negative present worth, like, so if this was 10% and this is 12%, you could approximate that curve with a line, but it's not exact. Yeah.
Okay.
That's a great question. All right, so what's this automated tool so we don't have to just poke at it all day long? Here under Data, tab, and then What If Analysis, and Goal Seek. So it gives us this tool where what we're going to say is our goal is for this one to be goal of 0, and then we're going to give it permission to change one thing in that worksheet, and the permission is it should change the interest rate. So when we say OK, it's going to keep changing the interest rate very quickly, and then it will stop when the sum of the present values is equal to 0. Okay. And you can see that, you know, it's found the answer to as much precision as we'd ever need. So that's the goal seek, and it was under data, what if analysis, goal seek. All right. Good. So that is, on the handout I've given you, it said that is the sum of the PV of the amounts is what we've just done. Let me go up to here.
Did you write the formula or you just?
Just the sums column.
All right, we've done the sum of the PV of the amounts. But there's also a function called rate within Excel, and it's even easier. So I'm just going to, here we're going to just do the rate function. All right, so here we're going to do so equals rate, and when you put in the parentheses, then it's going to start prompting you for questions. So NPER, number of periods. We could either click on a cell that has the number or just type it in. So there's 5 periods, and now it's saying PMT, like what's the recurring payment amount? Well, it was 16,000. And comma, and now it's saying what's the present value? And our present value is negative 60,000. And we can close parentheses, and it will calculate the interest rate that causes an equilibrium between the inflows and the outflows. And so see how it's the same here? Here's the rate that we calculated with this manual approach, and this was the one we calculated with the rate function.
Can you please go back, like,
Mm-hmm.
the formula that you put?
Yep. So it's equals rate. NPER is 5. The payment is 16,000.
Okay.
And then here under PV is negative 60,000. And so what it's going to do is it's going to solve many, many times basically the same thing that we just did. It's going to take each one of those 16,000s that are in the future, it's going to discount it to the present, it's going to combine it with the amount that's in the present, and it will keep doing that until there's balance between the inflows and the outflows, and it's solving for the interest rate that causes that equilibrium. All right. You'll get the hang of this, and so you know, if you didn't have your computer to follow along today, that's all right. Or if you did and it seems really bizarre and awkward so far, don't worry. You're going to become an Excel master in this class if you're not already. We're going to be using it a lot, so you'll become very, very comfortable with these financial calculations in Excel. All right, so the second problem of the in-class exercise is saying, what if we don't know the number of periods? We know P. So here, P is 60,000. We know A. A is 8,000. Now here, the P is an outflow. So keep that in mind, that that's an outflow, and the inflow is this annual amount of 8,000. So if the interest rate is 10% per year, how many years until the investment breaks even? So these factor tables are ratios of P to A. And so in our case, if we have A is 8,000 and P is 60,000, then the ratio of P to A, let me just erase the board here. P to A is 60,000 to 8,000 in this problem statement. So
you do the ratio and you look at the table?
yeah, we do. We try and find what's closest.
So it is
Yes? You're noticing the pattern, and that's good. So we get 7.5, right? 7.5 is the ratio of P to A. So in this P to A table, where is it closest to 7.5? It's between 14 and 15. So think about what the question is asking. How many years until the investment breaks even? So now let's think about this in practical terms. We've got an investment that we've paid $60,000. The contractor has paid $60,000 and then begins receiving all this new revenue over time. 8,000, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. If this equipment only lasted for 5 years, then the contractor is in real trouble because they paid $60,000 and they haven't got their money back yet. So what this question is asking is, how many years does it take if you're taking the 10% discounting of all the future revenues? How many years before the investment breaks even? Because you'd want the equipment to last at least that long. If its anticipated useful life is less than the number of years to break even, then you should not do the project. So that's what this is asking. It's saying how many years. And so if we look at the table, you can see that the ratio of P to A crosses over from 7.3 to 7.6, so between 14 and 15 years. And so between 14 and 15 years. How come we can't just say, how come we can't just have 7.5 years? Why isn't it, because if you multiply 8,000, yeah, I heard the right answer. If you multiply 8,000 by 8, so 8,000 times 8 is 64,000. So, isn't that good enough? You paid 60,000 and now you've recovered 64,000 after 8 years. So why isn't 8 years good enough? This is saying you have to go all the way to beyond 14 years. The break even actually occurs in the 15th year. So Jace, you were saying?
It's because you're not including interest.
Yeah, this doesn't include interest. This approach says that the dollars in the future are as valuable as the dollars that you paid at time 0. And future dollars aren't that valuable.
So could you, if you wanted to, just make F unknown? Like if it was like P and F, and just find F and then divide by it?
Well, no, because remember, F is a single lump sum. So 14.44 years. But remember, the end of period assumption says that that we get the amounts in lump sums. So the money isn't coming to us continuously. So in the 14th year, we're close, but we haven't broken even yet. And in the 15th year, we will have more than broken even. We'll actually have a little bit of profit. But you're right. If we solve for n, numerically, we'll get somewhere in the middle. So let's set this up. We've done it kind of the table method, where you're just looking at the ratio and interpreting the break-even year from when the ratio is too low to now when the ratio is too high. There's also a way to do on an Excel, if we've got that available. So up at the top, once again, we're going to have an interest rate cell. So I, and is it 10% in this one?
Yes.
So 0.1. And we're going to have year, amount, PV of amount. And then we're going to add one more column that we didn't have in the last one. we're going to have something that we call cumulative PV of amount. Okay, so we start at time 0, and we're going through, it doesn't actually say how long the equipment lasts. It's just asking when does it break even. So let's take it down through 20 years, because we've got the table for it. Let's just see if this lasts 20 years, what's the situation? All right, so now we need to translate the situation into a cash flow table where at time 0 we have an outflow because we're buying the equipment for $60,000. And by the way, just to save myself the time, I'm going to highlight all of these cells and I'm going to apply the formatting of currency. And if I do that now, then it will help me to see the amounts as I type them in. So I've just changed the formatting. It's an optional step, but I really prefer it. And then the revenue of $8,000 is constant every year through the end of the 20-year period that we're looking at. Okay, now this is where we're going to do that formula, the same PV formula which we saw in the prior example, equals PV, and now we're referencing the interest rate, and rather than typing in the rate, we could just type in 0.1 and the calculations will work. But if you want to change the interest rate, you don't want to have to go into each function and update the equation. It's just much easier to refer to a cell location, and then you could change the number that's in that cell location and it'll automatically update everything else. So that's why I think it's a good idea for us to click in the location and then we can type in the dollar signs or press the F4 button. So we're anchoring that reference. Now N, the number of periods that the amount needs to be discounted. So it's 0 for this one, it'll be 1 for the next row, and so on. And we're putting in a comma. Here we are in the payment field, skipping over it because we want this to be treated as a future amount. And we have to put that minus sign in because of how Excel automatically changes the direction of amounts in its internal calculations. So the minus sign, and we click on the amount, and that's the last thing. So we can close parentheses and execute. So obviously if 60,000 is already at the present, the quantity won't be changed at all. But this 8,000, when you find the PV of it, it's less because it's been discounted by 10%. 8,000 in year 1 is the same as 7,272 in year 0 if it's been discounted by 10%, moving it back. So this 8,000 is going to be worth even less. See how it's smaller and consecutively smaller? So these future revenues are getting pretty meager. $8,000 20 years from now has a present equivalent of only $1,189. So those future revenues aren't very impactful. Okay, now this cell is going to be, we're going to need to be careful about this cumulative PV of amount. The first year, it's just the amount. Do you need me to show you which one? The PV of amount?
Yeah, the PV.
Okay.
I don't get it from where did you get the $1 like in the formula?
I can do this one again, no problem.
Oh, thank you.
Yep. So equals PV. Okay, so the first cell is the rate. You click on the location that has the rate, and we're doing the anchoring with F4.
Okay.
And now the NPER, it's asking how many periods, and so that's the year. I'll click on the, for this row, the year, and then 2 commas, and the minus sign, and the amount.
Okay.
Yep.
Thank you.
And then once I have it here, I can just double click. See where it's kind of a little bit thicker in the edge? I can just double click and it performs all the calculations down through the rest of the data table.
Thank you.
Okay, now for the cumulative PV of the amount, the first row, it's just this PV of the amount. So it's just the same. But now, for the next one, it's the prior year's cumulative PV of amount and this amount for this row that we're on. So it's equals the cell above plus the cell that's to the side of it. And when you say enter, let me just center this. When you do enter, then it's saying, so far, at the end of the first year, you've recovered some of your original investment. At the end of the first year, because you had some revenue coming in, now the unrecovered investment balance is $52,727. So we can continue that down. How strange. I'm not seeing that thick, you know, how we continue the equation. There it is. Okay, if you ever see all these, that just means you need to make it wider. Okay, so let's continue it down through the remainder of it. And we previously said it was between the 14th and the 15th year, and this confirms that. See how it goes from negative to positive? So what that means is, if you're borrowing $60,000 to do this investment, you're going to have to pay interest on that. So every year you get some revenue, you keep some of the revenue, and you give some of the revenue to the bank. And so you're finally breaking even where you've got some profits that you get to keep after operating this equipment for the 15th year. So that's the N that brings equilibrium between the inflow and the outflows. All right, so any questions about unknown N? We've done unknown I and unknown N today. Any questions? Okay, well, that is it for today then. Remember that what you've got right now is homework 2, which you'll submit by Thursday. And question in the back? No. Ben?
There's a unknown interest rate for homework,
Mm-hmm.
and I know if I actually did it in Excel. You okay with us using Solver on the calculator?
Let me pull up that assignment because I don't remember the specific problem.
I think it's number 8 maybe.
Oh, you know what? I can pull it up here.
It is. I use Solver to solve it.
I just don't know if that's an acceptable way to do it.
Problem 8? No, which one?
Yeah, you're trying to figure out how much,
Yeah.
the maximum interest rate that you can afford to pay the bank.
Oh, you don't need Excel for that one.
Yeah, can we use Solver on the, like, do we need?
Oh, on your calculator?
Do we need to write it all out and solve it, or can we set the equation up and use Solver?
Well, I mean, you should put something on the page. I mean, so let's look at this problem specifically. So you've got 15 million total. So you've got 2.5 million. 2.5 million is being borrowed at 6.5%. And 5.5 million at 6%. And then the rest you will borrow from the banks. And so the rest, if we need a total of 15 million, is going to be 15 minus the 5.5 minus the 2.5. 7 million remainder. So 7 million. And then the interest rate is unknown, right? So X is equal to the interest rate that we can't go more than 10%. And the total amount that we need to borrow is 15 million. So I don't think you necessarily need to use Solver. I mean, this is just an algebra problem, really.
But what if we put it in Solver?
Oh, come on. If you want to, you can, but
I already did.
Yeah. Show some steps on the paper.
That's-
Help.
I got to that point, then I put it in solver,
Okay.
because it's quicker.
Because that's what you want to do? That's fine.
Yeah.
All right. Any other questions? Okay. See you Thursday.